Good afternoon, everyone. My name is Han Ding from TDD Institute. Today is a great honor for me to introduce Professor Frank Wilczek as the lecturer of the first class of the advanced topic in theoretical physics for undergraduate students of Zhiyuan honors program. By the way, I'm also from the 4点班 for 86 class. As you know, in physics, there are three major areas. One is to study something very small, like fundamental particles. The second is to study something very big, like our universe. The third is to study something very many, like solid materials. Most physicists focus in one area, even in one sub-area. But today's lecture is one of the very few who survey all of three areas and made extraordinary contribution to these areas. 50 years ago, in 1973, at the age of 22, only a few years older than most of you here, Frank, together with his advisor, Professor David Gross, wrote a paper titled Ultraviolet Behavior of Non-Abelian Gauge Theories, and offer a beautiful explanation why inside a proton or neutron, three quarks can loosely bond together, but no single quark can be freed from the confinement. Their theory discovered that the electromagnetic force which acts on a property called charge, the strong nuclear force which holds quarks together act on a property called color. Or you may think something as like a glue. This paper, together with a back-to-back PRL paper by David Pollitt, then a Harvard graduate student at the age of 24, made groundbreaking contributions to the basic theory, so-called QCD, for the strong force, a cornerstone theory for the very small particles, and helped three of them winning the Nobel Prize in Physics in 2004. Besides this beautiful concept of color, of QCD, Professor Wilczek has also come up with some exotic and beautiful concepts, such as axion, which has been considered as a candidate of dark matter of our very big universe. And another example is anion, which unlike fermion or boson, can have fractional charge and fractional statistics. And my own research, Majorana zero mode, is a special kind of anion. A third example is time crystal, a crystalline order in time, a different form from the usual crystalline order in space we see in the very many world. In addition to all these great discoveries, Professor Wilczek has also made a great impact in popularization of science, wrote a monthly Wilczek's Universe feature for the Wall Street Journal, and published several well-known books. I read his book, A Beautiful Question, in both English and Chinese version. And I found it is by far the best popular science book I have ever read. By the way, the Chinese translation is great. His latest book, Fundamentals, will release its Chinese version in a few days, this Sunday. And I would highly recommend these two books to all of you. It is a rare opportunity that young students like you can listen a towering figure in both serious science and popular science in a close distance. Through a serious lecture on advanced topic in theoretical physics, I hope that you can be inspired by the beautiful concepts in these lectures and also ask some beautiful questions. With this, please welcome Professor Frank Wilczek.
Thank you for that very gracious introduction, and welcome all of you. Thanks for coming. It's really inspiring to see so many bright young faces. And now I'm going to have to take a few seconds to get the technicalities under control. So. Okay, so I'm not sure this is going to work smoothly, but I'm going to try. We'll try. This will be a series of 8 lectures planned, and I should tell you what the plan is. This first lecture will be kind of unique. I wanted to give a lecture that I could give in my sleep, since I thought I might be sleeping after the long trip to China. It's going to be about quantum chromodynamics, QCD, the theory of the strong force, which was already mentioned. And I'll be talking about some old ideas, but also some very new ideas where QCD, I think, is still a vital subject that is evolving and that is giving ideas that will be carried over into other parts of physics. And then the second lecture will be a kind of colloquium about time. It's called Symmetries of Time, and it's kind of an introduction to then the more technical lectures, which will be the rest. I'll be giving a series of lectures, especially revolving around the concept of time reversal symmetry and its implications. One big part of the story will be the story of axions, which are meant to resolve some fundamental issues about time reversal symmetry in physics, and amazingly and very encouragingly turn out to also be an excellent candidate to provide the dark matter of the universe that cosmologists need. And then I'll be talking about time reversal in matter, and finally time reversal in biology, which is a new frontier that I think is very interesting and exciting. Okay, so without further ado, let's begin. Let's begin. Okay, so confinement made simple and then complicated. So confinement is a characteristic feature of quantum chromodynamics that I will explain what it is first, and then why it caused us a lot of trouble in the early days of QCD. But now, looking back, we can understand it in simple terms, and the question becomes to apply that insight to get a better description of matter in new circumstances. So that's the story I'll be telling, and I'll tell along the way we'll have several new concepts that will be introduced that I I made special words for so that they could be memorable. So real virtuality. You've probably heard of virtual reality. This is the converse. Sticky gluons. There's a glue which not only glues things together but also sticks to itself. Treeons, which are things you make trees out of, but also the things you make protons and neutrons out of in this context. And finally, the idea of flux channeling, which is a way of carrying over ideas that we develop in understanding sticky gluons to trying to make photons sticky and use the wisdom we acquire from QCD in controlling matter better. So this year was the 50th anniversary of my original paper that really helped to found modern QCD. And my students arranged a celebration at MIT here. And these balloons are representations of protons and neutrons with 3 quarks inside. This kind of picture is actually something inspired or that calls to mind the so-called MIT bag, which is a model of protons and neutrons where you separate 2 phases on the inside and the outside, and the quarks are trapped inside the balloon, inside the so-called MIT bag. And a characteristic of QCD is that although there's a lot of evidence for the existence of quarks, I'll show you momentarily how direct and dramatic that evidence is, we never see quarks in isolation, but always inside bags, either with quarks and antiquarks, those are mesons, or in combinations of 3 quarks that are baryons. And in general, the number of quarks minus antiquarks has to be a multiple of 3. That's called confinement. So you never see a single quark or a combination of 2 quarks, but you can see things that are made out of 3 quarks or a quark and an antiquark. But although you can't see quarks in isolation, you can see their manifestations very directly when you do experiments at high energy. So this is an electron-positron collision. All this red stuff is the machinery that makes that happen. So an electron and an anti-electron collide, and things come out, strongly interacting particles, things we account for in terms of quarks and gluons come out. But none of these are individual quarks or gluons. What they are is something called a jet. A jet is like a lightning bolt initiated by a quark or gluon, but the material that actually emerges is obeying this rule of confinement. So it's a protons, neutrons, mesons, maybe antiprotons, things like that, but never individual quarks. However, if you track the energy and momentum of all the particles in these jets, and you compare it to theoretical calculations of the energy and momentum patterns that should be left by quarks and gluons, they match precisely. So in a sense, you are seeing quarks and gluons here, not as individual particles, but as flows. The flows of the actual particles you see reflect in their energy and momentum, their angular distribution, also the number of quarks and antiquarks and gluons you produce with different probabilities. All of those can be calculated based on the reality of quarks and gluons, and then you see a successful comparison of theory and experiment. So in a real sense, you are actually seeing individual quarks and gluons, although you never see them at low energies. You see them in this indirect way. And that's the problem of confinement. How is it you can have building blocks of the world of the strongly interacting particles that exist in the theory, that are clearly manifested in experiments, and yet never exist as individual particles. It's quite different from atomic physics, where you can take apart the atoms into electrons and nuclei, and you can study the electrons separately and the nuclei separately. This tension, this unusual feature, is the problem of confinement. So the particles out of which we build the theory are not the particles we see, and the particles we see are not the particles out of which we build the theory. And some people still find this disturbing. We certainly found it disturbing in the early days when we didn't have confidence that the theory was correct, and those high energy experiments really didn't exist in a mature form. The evidence was nowhere near so good. So this was, oh, okay, thank you. All right. Good. This will be ready for the question session. All right.
For you, just
All right.
wait for a moment. Yeah. Okay.
Okay, great. So now, all right. And some people still find it disturbing. In fact, the Clay Institute in Mathematics has offered a $1 million prize for the proof of a weak version of this phenomenon. But physicists who don't demand proof or don't demand mathematical rigor in their proofs, I think by now are pretty well satisfied, and I'll show you why. So let's discuss this problem of confinement in as simple a way as possible. So here, we're going to discuss, instead of the strong interactions in 3 dimensions, the real 3+1 dimensions, the real thing, we're going to discuss an imaginary world of just electrodynamics, QED, in one space and one time dimension. And we'll see a very, very similar kind of phenomenon occurs to confinement. So we're following here the advice of Albert Einstein to make everything as simple as possible, but not simpler. So to capture the idea, and also the advice of a somewhat lesser physicists to do what we can get away with. And if things get complicated and look messy, that's often a sign that there's a better way to do it. So 3+1 dimensional non-abelian gauge theories sort of are considerably more complex than the 1+1 dimensional abelian gauge theory we're going to discuss, but they're gloriously difficult and have been a rich source of problems and phenomena that people are still grappling with, very much so. And but this key phenomenon of confinement we can discuss intelligently in a much simpler context, and we learn from it. We'll learn this concept of real virtuality. So this is Lagrangian density. Don't be frightened by this if it's frightening. This is just the way of encapsulating the Maxwell equations, or the basic equations of electrodynamics in 1+1 dimension. And this is the propagation of a spin 1/2 fermion in the presence of these electromagnetic interactions. But I've called it Q because it's meant to look like a quark. So the analogy is these photons in 1+1 dimension will be like the gluons in 3 dimensions, and the fermion, the charged particle, will be like the quarks. Okay, and then a little bit of technology. If we impose A1 equals 0 gauge, and if you don't follow this, take it as poetry, and you can fill it in later. Qingdang will help you. Then, if you do that, then the gauge field part contains no time derivatives, and we can use the equations of motion to eliminate it. So that's the derivation of a very simple picture that emerges when you analyze this theory. All the theory is a force. So in one dimension, if you have electrodynamics, there's no such thing as radiation. There's just a force. You can capture it all in terms of just a force between the charged particles. And you still have a form of Gauss's law that the amount of flux coming out of a particle is reflecting the charge of the particle inside. But since you're in one dimension, the integration of the flux is very simple. It's just constant. The flux can't go away. And so what happens is if you have a charged particle, an electric flux comes out of it that can only end on the particle of opposite charge. And that means that there's a constant electric field between these two. That means there's a constant energy per unit length as you separate these particles. So it's like a constant force. The energy per unit length is constant, so there's a constant force. No matter how far they're away, one is away from the other, it's a constant force. And if you think about it, that's the essence of this confinement problem. So the force, on the one hand, is inexorable. It never stops. So to separate a quark and an antiquark and isolate them would cost an infinite amount of energy. You very rarely have an infinite amount of energy. In fact, never. So the quarks can't be confined, can't be separated. But on the other hand, if the force is weak, and we're allowed to make the force weak in our thought experiments, then the force can be very, very weak. It's very weak, but it doesn't stop. And so that's exactly what we want to have in QCD. We have a weak force at short distances, but inexorable. So the quarks look like things that are physical, that have an existence, if we can look down to short distances or high energies. But they never exist as free particles. Their charge always has to be canceled somehow. So now let's sharpen that idea to bring out the paradox of confinement more clearly. So in this theory where we just have a force, we have these heavy guys and a weak force between them, but a weak force that doesn't quit. We can calculate, using elementary quantum mechanics, the wave functions of the bound states. We get bound states. Those are the analogs of mesons, which would be a quark and an antiquark in 3 dimensions. And what we find is that there are bound states with different configurations of the wave function of the quark and antiquark. Starting at twice the mass of the quark, and then because there's extra energy in the electric field going up a little bit, you find a spectrum of bound states with discretely different energies. All the way up until you have 4 quarks, and then you can produce 2 mesons. And so then you have starting a continuous spectrum starting from there. Yeah. But for this discussion, we'll mostly be focusing on the energies such that we're below that 4m. We're over 2m, but below 4m, so we have a discrete spectrum. So we can solve for the bound states using the Schrödinger equation. And in fact, I'll show you the derivation on the next slide. I won't walk through the algebra, but the idea is very simple. We can use the WKB method to analyze what these bound states look like. Because the force is weak, they can be very spatially extended, so they have many nodes, and that means we can use the approximation that there are many nodes, the WKB approximation, in order to get all but the few lowest states very accurately. And this is what one finds. The energy, in terms of the number of nodes, so counting up the states as they go up in energy, they go up like n to the 2/3, the charge to the 4/3 divided by m to the 1/3. And the splittings, therefore, you just differentiate with respect to n, you find that the splittings get smaller and smaller as n grows, so the states are getting compressed. And here's the derivation. It's a nice exercise that should be within the scope of undergraduate education to calculate the bound states using the WKB method. So 2 pi n is the integral of dxp. So this was something that even people like Bohr and Sommerfeld could have computed before the advent of modern quantum mechanics. Okay, so that's the picture that we get if we analyze the states of energy. Okay, so what does that mean for reactions? So as a thought experiment to see what this does for dynamics, for processes that occur in space and time, let's consider a process analogous to the E plus E minus annihilation, who's that kind of picture that I showed you earlier. Okay, so we have, these are the quarks and the gluons. The gluons have just sort of vanished to make a force. We have to introduce separately some fictitious things that'll be the electrons and the electromagnetic force. So we make an even more weakly coupled theory and let it couple in, mimicking the situation of electrons and positrons coupled to quarks and gluons in 3+1 dimensions that we're trying to model. And what you realize then immediately is a kind of paradox. When the energy is not one of these bound state energies, there's nothing to scatter into. There's nothing there. So the electron and positron don't notice that they're all these strongly interacting particles. They just propagate through. On the other hand, it's obvious physically, you just have these particles that are interacting very, very weakly with each other. You produce a particle and antiparticle. They should move freely. So this is the paradox of confinement, really at a very simple and tangible level. On the one hand, common sense tells you that the particles should be visible and propagate freely. On the other hand, if you look at the S matrix, if you look at a more sophisticated way of analyzing things, you find the paradoxical thing that, well, first of all, you find that actually these particles don't exist as individual particles, but then also that's reflected in the dynamics as a prediction that nothing happens unless you choose some very special energies. So how do we resolve these two very different, or reconcile these two very different pictures? And the reconciliation is very beautiful, I think, and instructive. It involves the uncertainty relation between time and energy, and also the basic concept in quantum theory of complementarity. So in elementary classes on quantum theory, you may hear that there is no energy-time uncertainty relation because time is not a quantum mechanical variable. So you don't have the same sort of thing as you have for position and momentum, where position and momentum are operators. You mess around and find this. You can't measure one accurately without the other. But I'll show you that there definitely is a time-energy uncertainty relation. And in fact, it's not different conceptually from the from the position-momentum uncertainty relation, fundamentally. And then as an application, we can resolve this tension between the S matrix on the one hand and common sense on the other. And the resolution is basically very simple. It's that the spectrum and the S matrix reflect the behavior of physics at infinitely long times. That's how the S matrix is constructed. It's kind of a limit of long time descriptions. And that's often a very useful approximation in the strong interactions where things happen very fast. So, but it's not a full description of how physics works, because life is finite. We're allowed to look at things that only last for a while. So let me show you this uncertainty relation. And since it's elementary and important, I will actually do the derivation right before your eyes. So if we have any two operators, so Hermitian operators, x, y, two observables if you like, that have a non-trivial commutation relation. So when x times y minus y times x is I times some other thing z. Let's first take out we're going to evaluate this in a state and show that this implies some minimal uncertainty in x and y. So to sharpen things, let's first take out the average values of x and y in that state. It didn't work. No. Okay. Next time. Okay. Okay. So now, with that understood, we evaluate something that's necessarily positive. We take x plus I times any real number plus y and multiply it by its Hermitian conjugate. So that has to be equal to or greater than 0. It's the square of this state from here to here, the absolute square. So, and then we just multiply it out. We have 3 terms like that. This is the most complicated derivation I'll be showing you in the whole lectures, because mostly I won't show derivations. And we assume this has, because it's equal to or greater than 0, it can't have any real roots. If this quadratic form has a real root, then it goes through 0 and goes on to the negative side. So we don't want that. And so we get an inequality that the expectation value of z squared is equal to or less than 4 times the expectation value of x squared and y squared. Okay. So the classic uncertainty principle is just z equals 1 here. In that case, this is a number, and you get 4 times the uncertainty in momentum times the uncertainty in position. Things like that are bounded below by a finite number as a fundamental reflection of the fact that quantum mechanical observables are represented by non-commuting numbers, things that when you multiply in different orders, you don't get the same answer. So now we apply that general relationship, so up there that we just derived, to the fundamental dynamical equation of quantum mechanics, which tells you that the time derivative of an operator, this is all in the so-called Heisenberg representation, so the states are fixed, but the operators change in time, then you get this dynamical equation. So we're using the very fundamental principles of quantum mechanics, the commutation relations and the equations of motion expressed as a commutation relation. And just plugging in this version of x, y, and z up there, you get this relationship, which is helpfully put into a box, which tells you that the uncertainty in energy times what looks like it should be an uncertainty in time if you just cancel the a's. This would be the uncertainty in time squared. It says that you need, but if you're going to talk about time, you have to have a way of measuring it. So you should think of A as a clock of some kind, of any kind. But whatever kind of clock you use, you can never defeat this limit in the uncertainty in how well you can tell time without bringing in uncertainties in energy. Okay? So that's the energy-time uncertainty relationship. By the way, the position observable, which is an observable in elementary quantum mechanics, is not an observable in quantum field theory. It's only an approximation. So if you really want a rigorous version, even of the ordinary uncertainty relation between position and momentum, you have to do something like this and refer to the instruments that measure the momentum, or the position, rather, the position. Okay, so now we know that to measure energies accurately takes a long time. Now, and then we recall that our energy spacings were getting very, very close together. That means if we want to resolve those energies, it takes a long time. Or reading it another way, if we only take a short time, we don't see those don't see those discrete energy levels. And so the paradox that came in from thinking that nothing happens unless you're at one of these energies goes away because the energy is uncertain. So the weird picture of dynamics that our thought experiment or the S matrix suggested to us, that nothing happens unless you're right at the crucial energies where there's a bound state, doesn't apply if you only measure in a finite amount of time, which is the usual case. And that's a relief because it violated common sense. So that was kind of a mathematical discussion. It's fun to visualize how this came about. How does the long time description build up into this paradoxical thing in such an elementary theory? And the point is that just think of what's happening in space and time. The quark and the antiquark separate. They don't feel much of a force. So they separate for a long time, slowly losing energy, and only after a while realizing that they're out of energy and they have to come back together. Okay? And then they keep doing that. Remember, the interaction is very weak, so they keep doing it. And they do it over and over again. And if we don't resolve events in time, we'll be averaging over many cycles of this motion. Or in space-time, it'll look like this. The quark and the antiquark separate, come back together, separate, come back together, and keep going like that. And this is very similar, now in time rather than space, to how you build up diffraction patterns or interference patterns. Because they keep coming, you have many ways of getting from the initial state to the final state that are averaged over, and they can interfere with each other. You can get destructive interference. So if you're at the wrong energy, where there's no bound state, you get destructive interference. But you have to wait a long time for it to build up, because these cycles are very, very slow. Okay, so that's how this paradox is resolved. And you can, although I don't think anyone's ever done it, it's a nice exercise to show how you can build up also by similar, a closer analysis, you could also calculate the actual wave functions based on this space-time behavior, at least in the WKB approximation. So the lesson is that freedom and confinement are a beautiful example of complementarity, that there are different descriptions of the same physical situation in quantum theory that are applicable in different circumstances, and you need both of them to do justice to reality. Here, freedom, which is what we get using the perturbative analysis of the theory, so you have a very weak force, that's just a fancy way of saying it's a weak force, is the appropriate description if you want good time resolution. So things move freely for short times because the force is weak. But on the other hand, the force builds up inexorably. And so if you want, and that changes qualitatively the energy spectrum. You get these interference effects, you get bound states, you get holes in the possible energies, and that's the appropriate description if you want good energy resolution. And you can't have both. You have, if you want good. Okay, so that's this, I hope, illuminating this model theory of where you have freedom and confinement in a way that's easily understood. Now let's go back to QCD with this in mind. So the essential dynamics that makes 3+1 dimensional QCD, the theory of the strong interaction, resemble 1+1 dimensional QED is that the essence of the confinement in 1+1 dimensional QED was that you had these flux tubes instead of electromagnetic fields going like 1/r². They concentrate and make tubes because in 3 dimensions, that's what happens in QCD. The gluons like to stick to each other. So instead of spreading uniformly, they make tubes. See, unlike photons in 3 dimensions or in 1 dimension, the gluons carry colored degrees of freedom. They carry colored charges, and therefore they are interacting with each other. Okay? Unlike light beams, which pass freely through one another. So thank goodness, otherwise our vision of the world would be very, very cloudy. The gluons very much feel each other, and so in fact, they want to stick, then they tend to be sticky. So asymptotic freedom, which was mentioned earlier, that was a big breakthrough in this whole story, shows the onset of that behavior because the force starts out like 1/r², but then gets stronger as you go far away. That's the beginning of the formation of this sticky tube. And I won't discuss this in any depth, but a strong coupling expansion is possible in QCD if you discretize it, put it on a lattice. And you also find this sticky behavior of of gluons and formation of flux tubes. But most of all, nowadays, with supercomputers, it's possible to just calculate the consequences of the theory. And if you look at the numerical solution, this sort of visualization was pioneered by Derek Lineweber in Australia. And you put in sources of color, so heavy quarks, like that, and calculate as a function of the distance what the gluon fields do. You find exactly that they form a tube. So this picture that was so simple and convincing in 1+1 dimension is also the basic picture that works in 3+1 dimensions, apparently. Okay, so the title of this lecture was Confinement Made Simple, Then Complicated. We've done the simple part. Now we're going to add a little bit of complication, which I think this is new and I think quite interesting and exciting. And the point is that one kind of one kind of charge is what you have in electrodynamics is very different from three, because if you have photons, they're electrically neutral, but if you have gluons, there's non-abelian symmetry, then they're sticky. But now we're going to look at this second inequality, that 3 is much less than infinity. Remember, the confinement was in units of 3. Number of quarks minus number of antiquarks is a multiple of 3. And so we have to understand that. That's very basic because we're built out of things that are things that can be built out of protons and neutrons, are basically 3 quarks. So it won't do to just have quarks and antiquarks. We also have to have a way of accommodating 3 quarks as building blocks of matter. And I've been working on this with 2 really excellent students at MIT. So this is a picture that appeared in the Nobel Prize poster for 2004. And it is wrong. Can you tell me what's wrong with this picture? What's that? A gluon. Yes, that's right. The gluon, that's one thing that's wrong, is gluons don't have the same kind of color as quarks. I think this is meant to suggest that this gluon has both green charge and red anti-charge. But you're on the right track. That one thing, well, what's wrong is that quarks don't have faces. No, that's not the only thing that's wrong. The point is that this is not how the force between quarks in this kind of configuration works. It's not, the flux tube doesn't extend between a quark and a quark. It would extend between, it could start on a quark and end on an antiquark. But if you have a quark and another quark, that doesn't work. Formally, there's a property called triality that's conserved. So that doesn't, but let's just look at the pictures from Lineweber again. And you see that when you have 3 quarks, they form this kind of junction, a Y, or they make a Y if you like. And that's how the force works. It's not. And here you see that this absolutely requires 3. That's where the 3 comes in to form this junction that has 3 lines coming out of it, which is not infinite and not 1. Okay. So how can we make a simple model of that? Well, we have several different choices. This was the choice in the wrong picture. If we just make charges, have 3 different versions of electrodynamics, make them separately. So a theory with 3 kinds of charges, and we put the charges like that, then it really would look like the picture. We'd have forces, mutual forces between the quarks, like that. but that's not QCD. We can do better if we have just one, I'm sorry, if we have 3 different versions of charge, and the quarks now have unit charge, so we don't have those tricky assignments, but the straightforward ones. And we add a new object, which I called a verton, which is charged -3, which can absorb all the charge and make a hub like that, which looks more like the picture of what actually is happening in QCD. Or that's 3 different versions of the emergent abelian theory. The best version, and even this can be improved, but it's more technical, the best version is to have 3 things with just unit of charge, so not 3 different kinds of electrodynamics, but just one, a fake version of electrodynamics, and then the treons, an emergent kind of interaction. And then the treon has charge -3, so it can terminate all the flux tubes and look like the picture that actually emerges in QCD. So the treon, which is the junction of these 3, is obviously a crucial concept in QCD. It's what allows us to have baryons, people. So let's see if we can take it seriously. By the way, treon, why is it treon? Well, first of all, in many languages, not Chinese, I'm afraid, tree, T-R-E, is the word for 3. So in Swedish, it's tre. Also, when you start to put these things together, they look like trees. If you have many quarks and antiquarks, join them up this way, it starts to look like trees. So I think this is a very good name. Okay, so if we try to take it seriously, the first thing is to see if it's actually correct. And to test it out in different experiments. Now, we can't actually do experiments cleanly without complications because, well, the strong interaction works very fast. It's hard to do experiments. And also, if you have light quarks, you can produce quark-antiquark pairs, and the flux tube will break. You can minimize the energy by having the flux tube break. So, but what you can do is take out the quarks as physical degrees of freedom, but have sources of color charge that play the role of quarks and probe the dynamical degrees of freedom, which are just the pure glue. So we're interested in how the glue behaves, but we can probe it by putting in different kinds of charges and seeing how the glue reacts to it. So the first, well, an early test of the treon concept would be the following. I should say none of these numerical experiments, which is what we're talking about, none of them have been really performed yet. So this is an agenda for future exploration. But I think the numerical experiments, they're certainly in the spirit of what Lineweber already did, and with modern supercomputers should be easily accessible. Okay, so if we have 2 quarks and 2 antiquarks and put them in kind of a rectangular array like that, one way to make the flux go would be this on the top. But if there's a constant energy per unit length, eventually, if the treon has a finite mass, it's better to do it this way. Have only 1 long flux tube instead of 2. So it's half the energy once you make the compensation for having produced this treon and little junctions on the 2 ends. So this will, if the treon is a real thing, we can measure its mass, and this is how you could measure its mass, by seeing when the flux configuration changes from this to this. We can do many other tests, however, to see if this concept holds up. And I'm anticipating that it does hold up, so I'll be very disappointed if it doesn't. So with multiple quarks and antiquarks, determining the optimal treon-antitreon configuration defines a very nice mathematical problem that generalizes a classic problem of mathematics, which is called the Steiner problem. Is if you have a lot of points, how do you join them with lines such that the distance is minimized? And since every length of flux tube is costing us energy, we want to minimize the distance to find the minimum energy. So if we calculate numerically the minimum energy configurations we still have to obey this rule of 3, since we can only get rid of quarks and triples. If you have 3m plus n quarks and n antiquarks, say, then we try to minimize the length to join them, subject to 2 simple rules. Directed lines go out of quarks and into antiquarks, and triples of lines can go into treons or out of antitreons. So we take our quark configuration, add treons and antitreons, and see, take a penalty for their mass and see what the minimum energy configuration looks like. And does it look like what emerges from the numerical simulations? Well, the first thing is if you have just 3 quarks, this is a classic Steiner problem. You're trying to minimize the length of a line that joins them. And this was solved a long time ago using the Euclidean geometry. And it's the so-called Steiner point where you put the treon. And it's a point such that the 3 lines that come out of it are at 120 degrees from one another. Let's see, that's not, I guess it's the, well, yeah, it's this, and this are all at 120 degrees from each other. And here's how you construct it. This is a nice exercise in Euclidean geometry. There are many ways to do it, but this is a particularly nice way. You make equilateral triangles on the 3 sides, and then connect each of those to its corresponding opposite vertex. And where the 3 lines intersect, they intersect in a point, and that point is the point where you should put the treon. Okay? So that's the prediction, and the numerical experiments will test this prediction to when the quarks are far apart. To minimize the energy, you should put a treon there. And you can do more complex things, of course. So here are what I think would be highlights of what happens when you do more complicated situations. So in the simple baryon, we had just 1 treon in the middle. We had this Steiner thing. But if you have 2 baryons, so 6 quarks, you could, of course, make 2 treons and hook them up that way. But that might not be the most efficient. More efficient might be to do something like this. So spontaneously create a treon-antitreon pair. So instead of just 2 treons, you have 3 treons and 1 antitreon. And this would be this is the prediction. Once you know the treon mass, you can calculate when this happens as a function of geometry. So there's a lot of confrontation between theory and experiment. Of course, the experiments are all numerical experiments, but you do what you can. Okay, and then time is, well, I'm over by more than h bar over 4, I think. So I have to start accelerating a little bit. So other interesting things can happen. You might have several equivalent ways or nearly equivalent ways energetically of putting down the treons. This is very much like in chemistry. where you have you have different ways of putting the bonds that are chemically equivalent, famously in benzene. So there are resonances. You can even, so this would be a threefold degeneracy when you have a hexagon like that. If you have an octahedral thing, then you can take you can make a treon here and on the opposite face in 4 different ways. And so you have a 4-fold degeneracy. And yeah, you can have a lot of fun with this. Here's how it looks in a numerical simulation when you have the 6 things, and then if you fill it out to an octahedron, you can make lots of pretty pictures. And that's okay. And there's a lot of theoretical entertainment to be had and fundamental issues in numerical QCD. If you have degenerate configurations, how does that show up in these numerical calculations? Presumably what happens is you'll over time you'll spend some time in one configuration and then another. How do they change as you run the simulation? This is very interesting stuff to people who find this kind of stuff interesting. And then to really do so this is what happens asymptotically when the things are far apart. The flux tubes form and take a shape which is not independent of their origin, but it costs them something to form, so you get corrections due to that. Also, very long tubes will start to wander a little bit, and that's called roughening. That will have to be taken into account. And then you can also check the basic idea that what is conserved is just the number modulo 3 of quarks. I won't go into this because of the limitations of time, but if you ask, I'll be happy to elaborate. So you can test the premises of this whole analysis and get more consequences by looking at not only quarks, which transform in the fundamental 3-dimensional representation of SU3, but by looking at things which transform in other ways, other kinds of charge. Okay, now I don't want to leave this out, so despite the time, I'm going to spend a few minutes to discuss this concept of channeling. So we'd like to discuss things like how treons interact with each other, but it's not easy to make that the lowest energy configuration. So there's an issue there. And similarly, we'd like to see how treons interact with flux tubes, and flux tubes interact with each other, and quarks interact with any of those. And there's a wonderful solution, an enrichment of this kind of analysis to addresses all those questions. And that's the idea of going from MIT bags to MIT pits, or MIT pits, or in more dignified language, restricting the flux tube into channels. How do we do that? These are all numerical experiments, but you'll see there are also real-world versions of this. So here's how we get treons to interact with each other, for instance. If we can force the flux to only be in a channel, then we can arrange that the different treons lie on top of each other. Okay. Remember, the Steiner configurations would have the treons leaping off to the sides, but if we don't allow that, if we don't allow the flux to hook up that way, we can force it this way. How do we do that? Well, it's very, very simple. In these numerical experiments, we can, in a way that's perfectly realizable, in fact, it simplifies the calculations, it's gauge invariant, everything you like, just put the coupling constant to 0 outside the channels. So we change the rules by making the background space-time inhomogeneous, and we can force the flux to be in channels. So we force the theory to be like a one-dimensional theory, which it wanted to be, but now we can also direct the flux. So here's how we can get the tube-tube interaction, how we can get a tube-quark interaction. We could also force the tubes to bend, see what their elastic properties are, and that could go into models of hadron behavior, or we can make them rotate. And there's a little joke that goes with that, but it's advanced English. This would make the pit and the pendulum. You have the pit moving like a pendulum. And there's a short story by Edgar Allan Poe called The Pit and the Pendulum, which is very famous in English. I recommend it. Okay, then you can also have fractional tubes. Remember, in free space, it was continuation of unterminated flux tubes that gave us the confinement mechanism. But if we effectively make space not infinite, so it's like having cavities in electrodynamics that confine the fields, then that infinity doesn't arise, and we can explore new questions. So here's an interesting one among many. So we have a quark, we have this mid pit, and the flux tube would like energetically to form in one direction, but now there's no symmetry to tell it which way to point. So what happens? Does it snake around? Does it just pick a direction and then maybe slowly in a numerical simulation move around among those degenerate configurations? I don't know what happens. So it gets really interesting. Also see if flux tubes can fragment into subtubes. Is that what they want to do, or does the flux choose to go in one of the arms and not the others? I don't know. Interesting question. Okay, so now let's turn from QCD or these numerical experiments in QCD to what we learned from it for more practical purposes. And G goes to 0, which is what we're implementing to make these channels, corresponds, if we look back at the basic Lagrangian density or the equations of motion, it corresponds to epsilon goes to infinity, that is the dielectric constant goes to infinity in electricity, or mu goes to 0 in magnetism. Okay, you may remember or may understand that the basic energy or Lagrangian in electrodynamics is 1/2 epsilon times E squared minus 1/2 mu times B, 1/mu times B squared. That's why it's this seemingly very different behavior is just a matter of how things were defined, but in either case, it means that there's a lot of energy to make the fields, and so the fields are 0. So that's the analog of making G goes to 0 in QCD. Now, are those things realizable? Well, yes, there's one very dramatic case. You can have very polarizable materials. You can have very good diamagnets, but most dramatically perhaps, you can have superconductors, which are perfect diamagnets. So in effect, they confine flux to tubes. So in a superconductor, you make channels of this kind just by drilling holes. You make normal regions where the flux can go, and the superconductor doesn't want to go. So you have channels just like that. And this is a way of transporting magnetic flux from one side to the other. So you can make a magnetic field over here and transport it over there. You can also, by changing the area of the tube, increase the magnetic field strength, because it's field strength times area that stays the same. Or you can make a flux lattice and do interesting things, creative things. Okay, but in view of the time, I won't go into these possible applications. And then finally, this is the very last thing I wanted to discuss. One can go back to the challenge. Yes? Okay, well, okay, let's save that for the end, and I'll come back to it. But you want me to make the concept of treeons more precise, which I. Okay. Well, I showed you the pictures, so it's not coming out of nowhere. It's coming out of those pictures. And trying to do justice to those pictures. And more basically, doing justice to the existence of particles that are based on 3 quarks. And why is it 3? Why can't you have 2? Why is 3 special? And we saw the arrangement that makes it possible. Let me just add one more remark, then we'll come back in the question session, in the analysis of solids, there's a concept called umklapp processes. You break translation invariance, but you have a kind of discrete translation invariance left over. And in very gentle processes, momentum will still be conserved, but there's a discrete momentum transfer that you can have that breaks the translation symmetry. The treeons are the umklapp processes of gauge of the SU3 gauge symmetry. They're where the flux can jump by 3, basically. I don't know if that helps. You asked for mathematically precise. If you want mathematically precise, then we have to go through these rigmaroles. But the imprecise definition is it's what's in those pictures. Right? And more pictures will be coming, so I hope so. Yeah, so they'll take on their life that way. Okay, so let's suppose that treeons are established and they have a mass, and that their mass is much larger than the masses of the up and down quarks, which is probably the case since the up and down quarks have essentially 0 mass. So now we can play the same sort of game that chemists have been playing for decades of so-called Born-Oppenheimer approximation, where we have heavy degrees of freedom, which kind of describe a structure that moves slowly, and then light degrees of freedom, which feel that structure and move around and make effective forces between the structural elements and, well, plays out in the whole of quantum chemistry. We can do the same thing now for the strong force. If we have these treeons, we'll be treated as if they're the nuclei of atomic or molecular physics, and the quarks will be the electrons. And the conceptual basis is very similar, although just the force law is different. And I think this can be a way of replacing the MIT bag by something better, with apologies to my colleagues in the past at MIT. because we know in QCD there's not really a phase transition between two different parts of the world that defines a baryon. They aren't like that. What they are more like is things that interact with this Y kind of interaction. And so maybe that's a better starting point. And especially now we have the challenge of describing neutron stars with the same kind of precision and richness that we describe ordinary stars with. We know the equations, they're the equations of QCD, but we don't know how to solve them in a practical way. This maybe could be a start. And because when the quarks are close together, the force laws are simpler, and you don't have this, and the treons kind of get more distributed, the approximation of treating the treons and the quarks separately using molecular orbitals, if you like, instead of atomic orbitals, gets more and more important to do. And I think just like ordinary stars are much simpler than the Earth, because we don't have chemistry, but just high temperature statistical mechanics, I think it's quite possible that neutron stars will turn out to be much simpler than nuclei, and experiments on gravitational waves and modern astronomy that are going to tell us much more about neutron stars will allow us to access this kind of behavior if we can predict it. So it's kind of a scandal in QCD that we know the equations, but we can't put them to work in describing neutron stars, and maybe this will give us an approach to that. So with that, I'll end this lecture. Thank you. Yes.
Okay. So I have well, I'm not working in this field, but still
Right.
I have a simple question.
Yes.
The strong force, by definition, is the exchange.
The strong force is by definition is the exchange of gluons. But you said there are attractions
At a
between
fundamental
gluons.
level, yes.
Yeah.
Yes.
But there are attractions between gluons.
Yes.
But what is this attraction?
Oh, it's the same attraction. It's in a
It's also a strong force?
It's the strong force. Yeah, it's all the same force. You can write down the equations of motion of Lagrangian in one line.
Yeah.
They look a lot like the Maxwell equations, but with indices that tell you that you have three different kinds of charge.
Okay.
And you have actually 8 different kinds of gluons with 1 unit of charge, 1 unit of anti-charge. That would make 9, but you take out the neutral one, which is...
Yeah, then that comes the next question.
So
And
then the gluons, they have a color and an anti-color, but they don't have 0, so it's not canceled.
And then
So
you
they
need
feel
more
each
gluons to exchange.
The tube is a collective thing made of many
Gluons.
gluons.
Okay,
Yeah, it's we call non-perturbative. You have to take into account that there are many gluons.
Thank you.
Okay. Any from students? Okay. Wei Ku. You can.
Frank, you in one of the engineering part of your talk, when you try to see the interaction between the gluon, you had a design where you can engineer a region where the permittivity is 0.
Yes.
Right. So and then at some point you propose that perhaps this can be realized with the help of superconductor
For
example.
magnetic fields, yes.
Right. So I'm a little bit curious. What is the length scale for this kind of engineering, and is that
In
compatible?
the QCD case?
Yeah. I mean, is that length scale even compatible with the length scale of superconductivity?
No. This is subnuclear.
I know, but I'm saying that in that scale, there is no superconductivity that will 100% screen the magnetic field. Right? That won't work. This is a long waveless.
No, the application to QED is on a different scale.
Right. So I was a little bit confused. What was that comment about superconductivity?
Well, superconductors are perfect diamagnets.
Right, but not in this scale.
No, not on this scale. No. Also, you can't make holes that small either.
Right,
No,
right.
no. I'm talking about macroscopic superconductivity.
So are you implying that there is a way to, for example, in condensate system, that using superconductor, we might be able to probe something like this, but
Yes.
maybe not exactly the real gluon, but the quote-unquote
it's not,
emerged
it's not even
gluon.
close to the real gluon.
Right,
It has,
but the emerged gluon with a similar algebraic structure?
What as the similar physical phenomenon
Okay,
of forming inside a superconductor. It's not a new observation. It's a very important property of superconductors that they want to confine magnetic flux.
right.
They want the magnetic flux to only be in a small region, so it makes tubes, and usually that happens in what are called vortices, which form spontaneously. So inside the superconductor, it makes a little normal region and makes a tube of that. But if you give it a normal region by drilling a hole, it doesn't have to do that work. It's just so this is sort of making artificial vortices.
Right. And then do you have a candidate for the potential emerged quarks or something like that?
They're electrons.
Electrons. So you're basically using EMN. You're basically talking about EMN in this case.
Yes.
Just U1 version of that.
Yes.
All right. Thank you.
Okay.
Let me take the advantage. Very nice talk. Entertaining talk to listen to this. But I have a few questions. But maybe let's start this one. I'm not very sure about this. Your treon, is that still a U1 analogy of one-dimensional QED, something like that? Or 1 plus 1 dimension?
Well, you could set up similar things in QED. You can also, of course, study QCD in 2 dimensions. And if you did it for 3 colors, you might get something like this. But it's the geometry is impoverished, right? You don't have these Steiner points or anything like that.
Yeah, but I'm just puzzling about the results, because if it's to take analogy to QED, there's some very fundamental difference between QED and QCD, right?
Right.
But not just one that you have mentioned that for example, a long range force, not just linear flux tube. And the other one is actually that was captured by MIT bag. That is if you talk about quark, the mass of quark actually is you can take it basically 0.
Yes.
And the bond and the proton is much heavier.
Yes.
So it's counterintuitive to atomic physics, right? The constitute is quantity of this mass. It's It's larger than.
It's very similar actually, because the mass of an atom is much larger than the mass of an electron.
Yeah, but that's that I understand. But you have if you talk about the atom, that you have the mass of atom is less than the mass of nucleus plus the electron, right?
Yes,
and that is that's because. But for the proton, it's opposite.
Yes.
So that is the basic one of the basic feature for QCD, but that is not captured by QED, right? This is what I understand. As I understand.
Well, if you just considered the electron force,
yeah,
then that would be a positive contribution to the energy, right? So that's more like what you have. You have it costs you something to set up the fields. Now,
yeah.
in atoms, when you have forces, when you have charges of opposite sign, then you gain something. And actually, it's quite tricky to understand that. But it's basically because you have infinite self fields, which get partially canceled.
Yeah. This is what I think.
But that also happens in QCD when you have mesons. I talked briefly about quark and anti-quark configurations. In that case, you can get the lowering of the energy, because that.
Okay, but I didn't get the point.
Right.
So that is one of the problems for QED, like.
Well, you have to be very careful about making analogies between QED and QCD.
Okay.
But and actually, QED in one space dimension is a much better model of QCD in 3 dimensions than QED in 3 dimensions is. QED in 3 dimensions is very different from QCD in 3 dimensions, but QED in 1 dimension is much more similar.
Okay, so let's come to another question. So
yes,
for the QED analogy of one plus one, let me say that like this one. So MIT back model is actually says something that the phase in the bag is different from phase outside, right?
Right.
So that means they have phase transition.
Yes.
But when you talk about
but there is no phase transition, right?
Actually, okay, this is what you
Okay,
do different stuff.
how about this way?
For the 1 plus 1,
We
QED,
leave
that's,
more time for students to ask questions.
Well, let me finish the question, and I'll give I'll give a very short answer. If you, well, okay. Well. Anyway, there are no phase transitions.
We hope 志愿 honors program student can ask more questions. This is your class. It's your right to ask questions. Okay.
Yep.
Yeah. Any kind of question is fine. Okay. Please.
Well, I just have some naive questions about the picture of treons.
Good. Yeah.
You said that if I have imagined a picture that two anti-clocks they
yes
tear a little apart, they won't have a treon at first, right? Because they are very
right. It only becomes advantageous when you pull far enough apart. And exactly how far apart you have to pull depends on what the treon mass is.
Okay.
So this is a way of measuring the treon mass.
Okay, right. I see. That's just the question I want to ask. That's when you tear very far away, then boop, they will become 2 treons. And I want to ask where does energy goes?
Any what?
Energy. Where does energy goes?
Where does the energy go?
Yeah, because you know that.
When you're moving these things apart, you're injecting or taking energy out of the system. It's not energy is not conserved when you do these operations.
Well,
you're exerting forces on the quarks and anti-quarks to move them around.
Yeah, but at that moment when 2 lines comes into a treon.
Yeah.
What does
at that moment? Well, at that moment they have exactly the same energy.
Okay.
It's very much like in chemistry, where people talk about bringing atoms together to make diatomic molecules. It's the same sort of consideration if you look at energy curves.
I see.
Yeah.
But if they have the same energy, why they prefer to be 2 treons rather than 2 lines?
It's lower energy.
But
because if you have 2 long lines with a given energy per unit length, that's a longer length than having just 1. That's So there are some end effects, but basically it's a matter of having 1 line as opposed to 2.
Yeah, but at that specific time when they come to a treon, they have the same energy.
Yes.
Yeah, but so at that specific time, why they prefer to be treons?
It wouldn't prefer. It would go from one to the other. You would have a superposition of those 2 in quantum mechanics. You'd have both things would be present.
Oh, I see.
That's an example of what chemists sometimes call resonance, but. So when you have degeneracies, indeed, you have to take both into account. So neither one is adequate by itself.
Yeah, very good. Okay.
Very good question. Thank you.
Okay, pass to the side. Yeah.
Well, thank you. I have 2. I have 2 separate questions on treon models.
Ask one at a time. Yeah.
Yes, and the first is that it seems to be an effective way to describe the behavior of QCD, especially in dealing with confinement state at low energy.
Mm-hmm.
Yeah. So, how do you get such a theory from Seoul QCD? Does it rely on numerical simulation, and is it only built based on sole speculation on the numerical result, or it is some natural consequences if you do some manipulations on the original theory?
Okay, I think what you're asking is, do we have an exact solution of QCD which will answer all questions? And the answer is, to that question, is definitely not. We don't have such a, so QCD, it's like asking if we have a solution to chemistry. No,
okay.
you don't have a solution that works in all circumstances to describe all processes. We have to use different pictures and different approximations in different circumstances.
Okay, I see. So then for the second question is, when you mention there are some construction called not only treeons, but also anti-treeons.
Yes.
So do you really mean that treeons are particles in the means that there are some harmonic excitation of some effective fields, and also how do you treat them, whether as a real dynamical phase of
Yes.
degrees of freedom or something else?
Well, this is a new idea. We don't know how far it can be pushed.
Oh,
I would
okay.
hope that as we build up our understanding of what treeons are, we can address questions like, can they condense? Could you make a Bose-Einstein? Are they bosons? Well, they're bosons, I know that. But can they make a Bose-Einstein condensate inside neutron stars? Could they crystallize? There are many, many very interesting questions, and we just don't know very much about them yet. So I hope it doesn't take 50 years, but this is going to be a new chapter in QCD, I think.
Okay, thank you.
All right.
Okay, we have a senior student.
Yes, a senior student. Frank, a very nice talk. I just want to add to this student's question. In fact, probably the question is how your treeons mimic QCD. Do the commutation relation or the Lie algebra, something
No.
They don't really go to each other, right?
We're not at that level yet. Well, we're nowhere near that level yet. We just, so we have to explore whether the whole concept holds up at all in these numerical works. And then what happens when you add light quarks, which could change things a lot. So, but to give a more definite answer, one thing you can do, I mentioned briefly that there's a strong coupling expansion. You can compute these things in a strong coupling expansion systematically. So that might turn out to be quite accurate. So,
Okay.
but I mean, it's the lowest order in strong is certainly not completely accurate, but gives this qualitative behavior of flux tubes and joining and so forth. In higher orders, you could address some of these questions. What's the treon mass? What are the finite size corrections? How do the different representations join onto flux tubes? All those things could be addressed in strong coupling. You can also put things in channels. So I think there are probably 5 or 6 theses that could be written on the basis by just calculating in strong coupling different aspects of this.
So you talk about the treon, and then people now talk about in QCD the tetraquarks,
Yes.
pentaquarks. In this picture, you can also construct those objects.
Yes, you could, but that requires, building in the light quarks, and is much more speculative than. So that's for the future.
Okay, from a girl. Very good. Yeah.
Maybe a trivial question. Is there some similarity between the formation of treon and the frustration in the spin? I mean, in the magnetic material, if there is some triangle lattice, and each vertex has a spin, and it will be a frustration. Is there some similarity?
Well, it's an interesting thought. I don't see it right off the top of my head, but maybe there is some deep similarity. The nice thing about spin, as far as making analogies to QCD, is that it's non-abelian. Right?
Oh.
When you add angular momenta, you don't just add the quantity of angular momentum. There are vectors, some vectors, and so there might be some interesting analogies to spin, but I don't see it immediately.
Oh, so at least
Good question.
Thank you. At least there is not some theoretical formalism that can describe this.
Well, there might be, but I don't know it.
Oh, okay. Thank you.
All right. All right. Thank you.
Okay.
Okay, and Professor Wilczek, I'm thinking that it's like my understanding is like the formation of a treon is a way to minimize the energy.
Yes.
And I'm thinking, do we have this analogy in momentum space?
In momentum space, well, the closest analogy I can think of in momentum space, there might be better ones, but as I mentioned, umklapp processes are similar in spirit, where you break down to a smaller group than the translation. So here, SU3 is non-abelian, so it doesn't give conservation laws. That you can't find charges that are conserved, except that in SU3, there's a center of the group which commutes with everything else. That's a Z3 symmetry. So if you think about 3 by 3 matrices with unit determinant, you can have cube roots of unity on the diagonal. So there is a conserved subgroup, and that the triality is the representation of that subgroup. So that's, well, okay. We could discuss it after. But what was the question?
I'm seeing it's kind of my inspiration is from that. For example, in superconductivity,
yes,
the phonon-mediated interaction is k-dependent.
Yes.
And in this QCD case, is like this flux tube, the force is in real space.
It's in real space, yes.
Yeah.
So the flux tube picture, as it stands, is kind of a static picture. Right? You do minimize the energy when you have fixed sources. But of course, in physics, things move. The quarks, the color sources aren't infinitely heavy. So you'll want to examine configurations also in which the flux tubes bend or oscillate and things. And I think one can do that with this channeling idea, and then maybe put that back into the effective theory that the flux tubes have internal dynamics. I mean, there's a whole subject that you may have heard of called string theory, which is about the dynamics of flux. And well, in fact, string theory originally was an attempt to describe the strong interaction. So what we would now call a flux tube in QCD is sort of the original string, and string theory can get very, very complicated. So yes, so when you get beyond these kinds of static pictures, many new questions arise. It's good.
Thanks. Okay, I hear this ending bear. So with this, okay. One short question.
There'll be other lectures, and maybe you can add. Okay.
Very short question.
So let me just say for the future, we'll have other discussion sections, and you can certainly refer to questions from earlier lectures or discuss something that has nothing to do with the lectures. I'll be here. All right.
So what is the mass of the treons comparing with quarks?
We don't know.
I'm wondering that in the old picture, we already have a conservation of energies without introducing the treons.
We have what?
Conservation of energies.
Conservation of energy, yeah.
Yes, when you're introducing the treons and they have mass, so where is the energy comes from?
Well, the treon is an emergent object that's basically a special kind of clump of gluons. So it's not a separate kind of energy. It's already in the theory. It's just that if you want an effective description at low energies, this is a good thing to focus on. So, yeah.
Okay. with this. Let's thank Professor Wilczek for this beautiful and stimulating lectures. Thank you very much. Thank you. Okay. Okay. We have 7 more such lectures. Please join us. Thank you for your coming here today.
Okay. Thank you. All right.
We learned something new.
Thank you very much for the very inspiring talk. Thank you. Thank you.
You just arrived.